I think we can start. First of all, let me congratulate everybody with the beginning of the fall semester. We start the work of our seminar, and except 2 weeks in the fall semester, we have seminar sessions, and the breaks will be caused by Ukrainian-Uzbekistan conference and Kiev York mini school. Okay, the first speaker is Ekaterina Glinyanaya with the talk devoted to semimartingale structure in coalescing flows. Please.
Thank you. So I will share my screen. Can you see it now?
At least that you trying to share. Okay, now it is.
Okay, I'm trying to okay, full screen. Okay, and I think, okay, we can start. So as you mentioned, I will consider the integral with respect to point process of the Arratia flow, and I will consider it as a and I will prove that this is a semimartingale and write there some representation. So let's start, and I would like to remind what is a Arratia flow. So mostly here we already talk about it, so I just slightly give the definition. So we consider a family of continuous martingales that starts from each point of the real line, and with time they do not change their order. This is the third property, and the joint behavior between any two trajectory is defined through their joint quadratic variation by this formula, and this just means that any particle move like a Brownian motion, and two particles move independently before their meeting, and after meeting they coalesce and continue move like one Brownian motion.
Do you think that the form of four is appropriate to conclude that they will coalesce after meeting? Usually it is written like the integral from 0 to t indicates that s is greater than tau, where tau is the moment of the first meeting, yeah? And this is a different thing. Do you think that it means that they will meet after they will coalesce after meeting?
So if here, if they coalesce, then for such definition, so we just, I think, yes, no, because here we, in this integral, we can detect the moment of their meetings, and after it, their joint quadratic variation will be as one Brownian motion. And due to
why maybe they just meet and then immediately goes in different size and so on? Cannot it happen? Why it cannot happen?
Because they are the Brownian motions itself, and so after meeting they should change order, but because of the first, the third condition.
But a meeting is the random time, and in order to use now that they are Brownian and strong Markov property, we have to prove that our system has strong Markov property, yes?
Yes.
Uh,
Okay.
So,
No, but the difference between two
Yes.
motions is a non-negative martingale.
yes, or this is good. Okay.
And I also wanted to add that for this argument that I was also thinking about, you need it to be square integrable, I think, for even the covariation to make sense.
Excuse me, can you repeat, please?
I think that XU also should be a square integrable, because otherwise covariation doesn't make sense.
Yes, surely it is okay, but that they are martingale with respect to joint filtration.
Yes,
Oh,
with joint filtration
it must be
must be
point.
added. Yeah.
yeah,
It
yeah.
must be added that they are martingale with respect to joint filtration. Then Georgi is right that after meeting they will tell us. For sure.
Yes.
Okay, now it is clear, and we understand that if we add this joint filtration requirement, it is enough to say that this requirement for condition 4 can be rewritten as usual as the integral from 0 to t indicator that S is greater than the moment of the meeting. Yeah.
Yeah.
Okay, let's go further.
Okay, so it is known that if we fix the finite interval of starting points, so I will consider the interval from 0 to u, then the at fixed moment of time, so here t is greater than 0, so then it is known that the set of points is a finite set. So due to this, we can define a point measure by this formula. So we just count the number of particles in the set delta at time t, if we assume that starting points are considered from interval 0u. So here u will be fixed for all my talk. Okay. So in my talk, I will consider the linear functionals of this point process, which represented as integral with respect to this point measure. So the main object of today's talk is such an integral. But in order to investigate it, it is much more easy and convenient to consider a finite set of starting points. And then we will use a finite, the dense set of starting points in order to approximate all points in the interval. So to this aim, I can define a point measure with index n that corresponds to the same. We count the number of points in the Arratia flow that at time t came to subset delta if we assume that we start from some finite number of points. And Now I consider the linear functionals of these measures, which represented in form of integrals. So here the integral with respect to this the measure mu n, just we sum the value of function f at this points of clusters. And my aim is to consider the properties of such process with respect to time t. So we can expect the property of this process as semimartingale, because for finite number of starting points, here we have a summation of values of functions of trajectories in our systems of martingale. So we can expect this structure. So I want to.
Here is essential that f is a smooth function. Yes.
Yes. Here I consider f, which is twisely differentiable with bounded second derivative. So for now, I will consider that everything is quite good. And it's can be seen that we can approximate the integrals of such form for measure mu t by integrals by measure mu with index n when we start from each point from finite number of points. But if we consider a dense set here and then we tend n to infinity, we will have the same integral. So we will use this property and to derive the representation of such integral. So I want to represent it as a semi-martingale. So I want to write the part of martingale and the functions, the function of bounded variation. So this is the aim of my work. So I want to prove that such integral is a semi-martingale and find its Meyer decomposition. And here I would like to notice also that if we have a continuous bounded function f, then integral will have a bounded jumps. So it could have jumps, but they are all bounded by maximum value of function f.
You do not need 2 in front of maximum.
Huh? I don't need.
You do not need two maximums, up and down.
Maybe
it cannot jump simultaneously. Yeah, up and down.
Because it's continuous.
Yes, f is continuous. Katerina,
Okay,
maybe you can give us idea why it is so.
The idea again, we consider the integrals of I use the approximation, and for such form, if we consider the difference, then we can have a jump only at the point of adding new when two trajectories coalesce, right? And the value will be just f from x. So if I write the difference, I will have the summation. Okay, if I have the trajectories like this, and I consider 2 moments of time. So I add the values of like this and here. So when I will consider the difference between t and s, so the difference will be just on one value of function f.
I don't agree with it because it may happen they first hit very high and they just can move very low, but I don't think this is very important.
I don't understand high and low.
Suppose we in a situation where there are only two particles survived. That survived.
Yes, but I think that we have jumps only at the moments of the coalescing.
Yes.
Yes, so I think there are two particles very high, and they coalesce, but coalesce very low.
And it does not depend how fastly they coalesce. We have jump only at the moment of coalescence.
Yes, I do not mean about times, about position. Suppose they first
Yes.
they went very high, so f. Suppose that f is monotone, that f is positive and very high.
Yes, but they both goes to the same value. Yes.
Yes. Here, when I dance t
before jump, the values are very close. So
No, because if you have
jump, we just lost one.
But this integral with the point matters. So these are like values of functions.
Yes.
Exactly.
Values.
And at the moment of the coalescing, the values of function which coalesce are almost equal. And then one of these values disappears.
I mean, we have sums of two terms.
Yes,
right?
exactly. Two terms and
before
they became to be equal. Yeah.
So
yeah,
they are equal, and we have one more that will not
one of it. Yeah.
Just one of it. And
yes, but suppose that they were above the zero line before they meet. So we have like some two positive numbers. But when they meet, they are deep below the line. So they are.
But they cannot jump below the line. They move continuously. Yeah.
Yes, but they both just moved down.
Yes, and they meet, and it does not matter where they meet, under the zero, above zero.
Yes, but I mean, firstly, they have two positive numbers, this f of xi, and they have just one number, but very large negative.
No, we cannot have this just one number. We still have two numbers, just zero and something. Yeah.
But after they coalesce, we have just the value function of.
Yes, and if they reach value of function zero, then again the difference will be at least exactly for this value of function. Yeah. Because the large negative number is also value of our function. Yeah.
The value.
Yes, but the difference may be 2 times the maximum.
No. The size of the jump is exactly f of x.
Yes, one f of x. Yeah.
1 f of x.
One which we remove.
Yes, there was two. Fx. Oh, it's continuously. Oh, okay. Now I get it. Thank you very much. Now I get it.
Let's go further.
Okay, I have one question. We
Okay.
integrate with respect to R, or we integrate with respect, so the set of integration is U. Is it correct?
Here, let me draw the picture. So we start from interval 0u. So our process starts from 0u. But we integrate over all R. So here we have time t, like this. This is time t. So we integrate over all. We just sum all this f at this point.
So,
Yes.
So can I,
So here R.
well, okay, and so here, so is delta from B of R or
B of
from
R, yes, B of R, because I fix their starting point. So we start from here, but I can take their delta somewhere here, and I ask, do I have here particle that come from interval 0u or not? Is it clear or
no?
no? So I start from
What is the matter of question?
The question, it seems to me that we have to write here not R but U.
No, because we start, we define. You see, here is definition mu tn in the upper line, and this definition, this measure counts the points which survive up to the moment t, and counts its position, their positions. Yeah.
And mu also counts points that started from.
Yes.
From this interval, but they can go somewhere.
Yes, I understand.
Here, yes, on the previous. So I fix this interval 0u, so I consider the Arratia flow that starts from this interval, and it can move whatever it wants, and it can reach any set.
Okay, let's go first.
So now I would like to introduce other measure that in which term I will express Meyer decomposition. So to do this, now I will define the measure mu tilde, which is the position of discontinuity of the Arratia flow. So on the
now this measure is on the interval 0u, yes? Because you start from it.
Yes, here. Yes, here I forgot to.
Okay.
Right. So here now delta is subset of Borel on 0u.
Okay.
So on the picture, what do we have? Okay, we start from the interval 0u, and at time t, we will have approximately such a picture. Okay, time t. So I look just the points of discontinuity. I can write. I can found them here. So this is the points like these 2 points will be the discontinuity of this for this case.
So if we start by dual flow at the moment t,
Uh,
then exactly the the points which survive will be the points of discontinuity of the initial.
Yes, that's right. That's right. So for fixed time t, they have the same distribution, but the main difference, if I start to consider the integral with respect to such mu tilde, then the process will be a process of bounded variation. So this is the main difference, and here the idea is that here again we write here the sum of values of functions at the point of discontinuity, but with time they do not move like Brownian motions. So the points of discontinuity, they just appears and don't move.
But the question here, can you just go back
Okay.
to this? The question here is in the definition of this integral, because we understand that when t small goes to 0, the number of points of discontinuity increases, yes, and increases
yes.
up to infinity. So
Yes.
maybe you have to say something. You have to say something about the existence of such, or you just consider it.
Yes.
Or what is the bounded variation on the open interval?
So yes,
I
maybe
don't understand what this does mean.
here, yeah, this maybe not as it should. I should write here the some t0. So from t0 to t.
Oh, it is clear. Then it is clear, and this is because of the points of discontinuity disappears when t goes to plus infinity. Yes.
Yes, yes.
Because particles in Arratia flow just glue up one with other, and then the number they disappears.
Yeah. So
Okay.
this idea that you just mentioned, I write here. So you write that we have such include that the points at time t, they for bigger time t, they the set is not bigger than the points of the discontinuity for smaller time t. So it's easy to see that if we consider non-negative function, then we will have just non-increasing function. Integral will be a non-increasing. So after this, we get the result.
Okay.
Okay, so
Okay.
Now the next object that I would like to recall, this is the integral with respect to the Arratia flow that was introduced by Andrei Anatolyevich Dorogovtsov, and in order to describe it, we start with a dense set of points in the interval 0u, and we consider such random moments of time. So this is just tau k. Tau k is the first moment of heating by trajectory that starts from UK. Sum of trajectories that starts from the points with lower index. index here just. And for then, if we consider the sum of such integrals, so here we just integrate by trajectory of the Arratia flow up to its random time tau n. So therefore it needs some trajectories here. And then if we sum over all starting points from dense set, then such series converges in L2, and the sum does not depend on the choice of dense sequence UN. We will use the short notation for such integral of such notation, and in the same way it is possible to define just the integral not with respect to the trajectory but with respect to time, and the same we will use such notation. So note that we here do not write the integral with respect to u. We have two integrals, but we do not write du, because here this tau u is plays role of this du, because a lot of points, the main number of points will coalesce almost immediately. So here tau u will be small for huge number of starting points. So that is just the idea. Okay, so I will have in my in the Dubh-Meyer decomposition, I will have a term of such form. So I would like to prove here that this is a continuous martingale. So to do this, it's not hard. We first consider the approximation by considering a finite number of starting points. And if we consider the difference, so we just represent the summation in such two terms. Then the first, and then we consider the conditional expectation. Then the first term is measurable with respect to sigma algebra f at time s, and the second is equal to 0. So here is usually we can prove because the difference of x is independent with respect to sigma algebra at time s. And so M is a martingale. To see that it is a continuous martingale, I consider the difference and calculate it a quadratic variation. And after taking the second moment of quadratic variation, we get their estimation with difference of t and s2 square.
Excuse me, so you get that this martingale, okay, this second moment of the quadratic variation, so it is like fourth moment, yeah?
Yes, yes.
Of the initial, okay, good.
So okay, so now passing to the limit, we will get a martingale, but in order to prove that it will be a continuous again, we need to notice that it is this sequence martingale with respect to common filtration. So we can, if I consider this day, then I will just use inequality for supremum of martingales.
Mm.
So here just use that the difference of two martingales with respect to the same filtration, again a martingale. So this is allows us to see that choosing the subsequence of indices, we can see that we will have a continuous modification for the limit.
I think that if you use Burkholder-David Gandhi, then you even can say that they converge in square mean with respect to uniform distance in C0, 0,1 or C0, T capital. Yeah.
Yes, this is also.
You can shot by you can shot two rabbits. Yeah.
Yes.
Continuity and quadratic integration. Yeah, but it's okay.
So we have this part. So now I have.
I'm sorry, I have a very small remark that that this integral is a martingale is a known fact. I think it's stated in the original monograph, but your proof is obviously different. Just historical remark.
Okay, thank you. So now I can consider the process and write its Dürr-Meyer decomposition. So the integral has such representation for martingale. For martingale part and a function of bounded variation. So let's see what is what here. It's quite huge, but okay, for martingale part, it's not huge. It's given here. It's quite simple. So we have the integral with respect to the Arratia flow that we just discussed, and for a function of bounded variation. So here the refers to summation. We have the integrals with respect to u, but we then integrate only those trajectory that survive before time t.
Which meet with some other before time t, yeah?
Which meet, which meet with some others before time t. And here we have the integral with respect to measure, to point measure of points of discontinuity. And here just integral with respect to ds that we define just on the previous slide.
But can you just go back for a moment? In this form, again, the question which we mentioned slightly today arise. You have the integral from 0 to u capital f u mu t du. So it is defined up to the for any positive t, yes?
Yes. So,
right. Is it clear that it doesn't blow up or compensated by some other term maybe? So what is its behavior near the point T, because we say that
Near
this is
the
from
zero.
bounded variation, and now it must be bounded variation, maybe on the interval from 0 to T, yes.
Yes, so maybe let's consider for now not on the interval from 0 to t, but from some non-negative or from some positive t. Yes, so
Okay, so you start from positive t.
yes.
Okay, let's go further. Let's see.
I have a question about notation. So the first very integral from 0 to u indicator. Does this indicator mean something, or you can just write integral from 0 to u, integral from 0 to tau of u minimum t? Because
No.
this is a difference.
Yes.
This is different. We just count those trajectories which already meet some other trajectory before time t.
But then this is a different integral.
Yes.
Yes, this is a different integral, but still it converges. And
So these two, like this one and this one, they're different. Yes, they're different because
So
we integrate just up from 0 to tau of u. But here, if I consider the time t here, so tau is bigger than t, then I do not consider that the integral with respect to this trajectory at all.
tau u, I mean, what is tau u then? I mean, I don't understand. I'm sorry, but I just don't understand the definition of this integral. Maybe if you show me the definition of the original integral and right beside him.
Okay, let's go back to the definition of the original integral and explain. Yeah.
I just don't
I need to. Okay, original integral. Oh, like here. So here, if I so this is the indicator. If I write here just minimum t, I add here minimum t, right?
Yes.
And if you write indicator, what is the definition?
But if I write, so it's clear. But if I write here the indicator, that one, so I just here multiply by the indicator that tau or n is less than t. So I consider,
if you consider sufficient points, there are more and more those that tau n is less than t for fixed t as n goes, and the number of points increases.
Exactly.
So
yes,
this integral,
why does it exist?
Because it's smaller than if I don't write it.
Yes, but it doesn't mean that the limit necessarily exists.
Not smaller, because it may be negative.
A number of summands we have. Okay, number of summands is less than in this. So if in this case, number of summands is.
But I'm not sure that the series is absolutely convergent. Is it?
It converges in square mean, but absolutely converges in square mean. So
I remember that one of the main problem was that, I mean, Andrei Anatolyevich, when you define the integral, that it doesn't depend on the partition.
exactly.
Yes, it's not clear here, for me at least, why it doesn't depend.
It is clear if you write the picture. Oh, maybe I can write. Let me try. At least I have sign of the packet. Oh, yes, I can. You see, here is our interval 0, u. Now let's write this usual for us picture of the coalescing trajectories in Arratia flow up to the moment t. Then what we count? If we agreed that we define tau n as when we glue up with the upper trajectory, then we don't count only we don't count only this trajectory because we don't count only this trajectory. So we exclude, exactly as Nikolai said, we exclude only a finite number of trajectories from this sum. All other trajectories remain to be present in the sum, and the rest, of course, converge. Yeah. At least in probability. Yeah.
Yes, thank you. It's clear.
Yes.
But it is no longer martingale, right?
Maybe I don't know.
So
No.
that's why, because you included it in the part with bounded variation.
Yes,
Yeah.
it's not a martingale.
So this is a different. Well, it does seem like a very different thing, because if this martingale property is lost, at least it's a very shallow.
It can be, you see, the behavior is different because when you move from T to S or from S to T, so your integral here like this, let's add, I wanted to draw it here. Yes, let's do something like this. Okay. So I don't write here minimum tau t, so I just count order. So if I consider the finite number of starting points, so I add just what I add this trajectory, so integral up to this, I have some random variable. Then I do not count this the integral through this one, I do not count, and so on. So here I have the sum of random variables. Yes, for
well, that was true for the first integral too.
yes, and here when I consider two different moments of time, then my sum is just it differs by one random variable, which is the integral over some trajectory up to this time. So
Okay, Katya, maybe I can say something. When we discuss this integral with Katerina, we agreed that this integral is much similar to the integral with respect to point measure in the space of trajectories. We just have the point measure which is generated by our trajectories, and we have pieces of trajectories up to gluing with some upper trajectory. Then suppose that they disappear, and then we have such pieces, and we just count them. And the larger our time t is, then the more
they
pieces,
appraise.
more pieces we add. So this looks like we have the integral with respect to a random point process, but in the space of trajectories. This is maybe explanation why we expect that it is bounded variation, and why Katerina count it in the part of bounded variation.
Yes.
I would like to ask just one short question. I will make a picture, so just tell me, do I right or not? So assume that you have this Arratia flow and a time, and say another time, they coalesce. So if we integrate until this time, so we integrate over these trajectories and this, but we don't integrate with respect to this.
Yes, and we don't integrate with respect to this, excuse me?
This green, yes? So we integrate only blue, but we don't integrate green.
Yeah, more or less, yes, but you have to write green up to this moment, because
To 0. To 0.
up to 0. Yeah.
What do you mean up to 0?
Like
because
here,
we have
like
the
up to this.
agreement that if we have two trajectories, then
So we don't integrate this and we don't integrate this?
Yes, like
yes.
this. I write.
We
And this?
integrate over this. But if this does not merge with some other up to the moment t, we don't integrate. So we integrate this one, we integrate this one, everything which we, it is like in the barber shop. You just cut hair by this trajectory, and don't count it.
So if you have a trajectory that doesn't meet any other, it's excluded.
Yes, and
Yes.
we have a precise definition of the meeting. It must meet trajectory from above. Yeah,
From above, yes, it's not symmetrical.
exactly. Okay, can we go further?
Yes, I just deleted.
Okay.
So the idea of proof is again to consider the approximation with finite number of starting points. Or I'm sorry, where am I? Oh, here, yes, finite number of starting points. And for this, the representation is slightly different, and we will see that what I showed before we can get as a limit from this representation. So here, the martingale part is again the summation of integrals with respect to trajectories, and the part of bounded variation is of such form. So here we sum the value of functions at all points, but we subtract the value of function f at the position of the Arratia flow that starts this point at moment of its coalescence to upper trajectory, if the moment of coalescence less than t. In other case, we do not subtract this term. Okay, so how to see this representation? The integral with respect to point measure that counts the clusters with starting from finite number of points, we can represent as this sum. So we just count those values of function f at points of the Arratia flow who survive before time t. So tau is greater than t. Those who coalesce with someone, we do not count them here. And now for each summand, here I use the eta formula for the product. So now f is is a good function. So I write this beta formula, and here I have the different integration with step function, which gives me the value of function f at point of coalescence, just for those tau which are less than t, this value. And here I have the integral with respect to differential of f, so I just represent it by eta formula again in order to have the later their integrals with respect to Arratia flow and just ds. So after summation, we will get this formula that I represented here. So I write it here. So next step is to consider the limit when number of points tends to infinity. Of course, I consider here a dense set ui. And the main problem here is to deal with this term, because there are others will converge to integrals that defined by Andrei Anatольevich. So I consider this summation. So here, as you see, these terms compensate each other, because if I consider just summation of f of u, it will converge to infinity. So I should consider them together. And I split them in such form. So I just add and subtract this term in order to get together f of ui minus f of value of Arratia flow. So let's consider the first sum, this S1 of such form. And again, using eta formula, this brackets, for these brackets, I can write as integral with respect to Arratia flow and dr this time. So then substitution for s moment tau for each summand, I will have exactly this summation that we discussed as a limiting of to get the limit for I'm sorry. Okay. So now we pass to the limit, and we get these integrals that we already discussed. And it's easier step to consider the other terms here. So for this part, we will have the integral with respect to measure of points of discontinuity, and the limit we can express like this term. So we have this formula for the limit for this summation.
Mhm.
So this is the proof of the statement, and if you have some questions, we can discuss, or I can move forward if I have time. So
Maybe it's better to go forward, and then we will have some small time for questions. Yeah.
okay, so this is a next step in investigation is to to apply such an integrals to investigate Arratia flow with drift. So here I give the definition of the Arratia flow with drift, and in as it in informal description, we just have the not just a Brownian motion with coalescence, but we have such a drifted Brownian motion by function A here. And it is known that the distribution of such a process is absolutely continuous with the distribution of the Arratia flow X, and the density is given by this exponent. So now, in order to investigate the corresponding point process of the position of clusters that I will denote by mu A. So if I would like to find the expectation of linear functionals with respect to such point process, I need to find the expectation of such product. Here, I of t, my integral that we investigated before. And here now we know that I is semi-martingale, so we can apply eta formula. And after this, now we need to understand what is what here. So differential, the integral with respect to exponent is not so hard, but the main problem is to understand what is the integral with respect to integral. So I is integral itself. So I want to write the expression of the integral with respect to this semi-martingale. Of course, we got the representation for function of bounded variation and martingale, but I want to write the answer in terms of integration with respect to Arratia flow. And here's the lemma. First, I consider the representation of integral with respect to integral for point process that starts from a finite number of points. And here, maybe we can look on the last line. There, one integral that just the integration of function psi with respect to df. F, this is my integrand in integral I. And the first is, I consider now, here appears the same as we saw before. So here we have the difference. We have the difference of the function at starting point and at the value of meeting time. So maybe the proof is not so hard. Again, I use this do maybe decomposition and integrate with respect to b and m. So the integral with respect to this function of bounded variation has such form. So here we just need to integrate with respect to such a step function. So here this is some random value and we have a step function here. So I do this and so we will have this answer for this part. And the same, the integral with respect to martingale part, so it's not hard. So we just use this representation and we have usual integral with respect to Arratia flow. So the next step is pass to the limit. So I got this formula and hope it's correct. So I just passed to the limit in the previous expression here that we got. And here we will have the integration that maybe not integration. Sorry, here maybe I write a little bit. Yes, so by passing to the limit, we will have so the main problem again is to pass to the limit in this term.
I have a small remark that also passing to the limit when you integrate, you write this double integral with respect df x also seems to require some work because df is actually a sum of two integrals, right?
I'm sorry, f is
df of x of us, you're integrating with respect to this expression. It's obviously defined in terms of
yes, yes.
It's a sum of two integrals, essentially.
Yes. So this is just a short representation for such form, like the f prime dx plus 1 over 2 f2 prime dr. Yes, so here the integration, yeah, I understand the question. So here the differential with respect to s.
Yes, because for me it's like you said, it's kind of hard to catch.
Yes. So I just use it for short notation and
yeah, it doesn't seem trivial to me. Whatever.
Okay, so passing to the limit. So here, when we pass to the limit again, we have so this term will converge to this one again. The differential with respect to time as here and here. Then after subtracting one from another, we will get the difference of psi at time s and point of coalescence. So I think that this is all. So I represent the I prove that the integral with respect to point process is semi-martingale, and I tried to represent the integral with respect to this semi-martingale. That's all. So thank you.
Okay, thank you very much for interesting talk. Hope you will not get flu during this talk. This is time for questions or comments, please.
It would be interesting to understand properties of this integral when you have indicator inside, because it seems to me it is not a semi-martingale. Well, it is not a martingale probably.
Yes.
But maybe a semi-martingale, so it would be, well, so it's interesting how to work with it.
Besides.
Yes, we considered it, and I think that the point of view on it as an integral with respect to point measure in the space of trajectories will be fruitful. Yeah.
And I want to add that that's why exactly because of what Professor Plipenko said, it's not, for me, it's not clear all this passing to limits immediately. So maybe there are some arguments that should be added, possibly.
Oh, of course. Oh. Yes, here for the last step, I didn't, maybe I skipped this step, but for the Dubmi-Bayer decomposition, yes, it could, I think I did it, so yes.
Okay.
I am not saying it's not true. I am just saying that.
Yeah, sure.
Okay.
Other questions, please. I have a comment that actually our original aim was, as Katerina said, to investigate the points of coalescence in Arratia flow with drift, and we hope we will do this using some formulas based on the integral with the stochastic exponent of Arratia flow. But also, it seems to me, actually, this question is not only for Katya, that it will be interesting to see what is the coalescence structure in the Harris flow. Because we remember that in Harris flow can have actually ugly covariance function like exponent minus absolute value of x in alpha power, and this alpha can be less than 1. So one can expect bad behavior of all this of some of these paths in Dubmi decomposition. So even in the construction of the integral with respect to Harris flow, like with respect to Arratia flow, of course we have to be care about the Matsumoto condition of coalescence. Yeah. So it will be interesting maybe to add this for general Harris flow.
I have to say that not the case of Harris flow, as far as I understand, is much hardened, exactly. As far as I recall, it wasn't even able to define this exponential.
Yes, so this question not only for Kate, but I
Yeah, I
think
understand.
that something can be done in this direction, and it can be it is a matter of interest. Okay.
I just have to say quickly that the original proof of the existence Harris flaw was the existence of this coalescent structure depended on Feller's one-dimensional diffusions, and it kind
Yes,
of doesn't scale to directly to multi interactions.
Yes, I recall this Matsumoto condition. Of course, we have to be careful
Yes,
about
exactly.
it and consider only such covariance function, which momental covariance function, which satisfy this condition. Okay, if there are no other questions, then thanks to speaker again. And Georgi, know who will be the next speaker?
Yes, Professor Pilipenko.
Oh, okay. Okay, so thanks everybody, and see you next week. Bye.
Thank you.
Bye.
Bye.